Reproducing the spatial distribution of haptic stimuli in virtual reality is crucial for enhancing the realism of the experience. The artificial creation of spatially distributed haptic stimuli has been extensively studied. For instance, this figure illustrates a high-resolution haptic display using suction pressures developed by the authors. Haptic rendering of the spatial distribution of contact forces is also crucial for the effective use of haptic devices. Researchers have developed real-time calculation methods to determine the pressure distribution resulting from the contact between a finger and objects. However, physically based simulations face challenges due to the computational burden and errors arising from the difficulty in creating sufficiently detailed models of finger biomechanics. In this study, we propose a data-driven method for rendering pressure distribution based on actual data collected from experiments with real fingers. During measurements, a finger is pressed against a capacitive pressure sensor array, which consists of 16 rows and 15 columns. We obtained pressure distributions under various displacement and contact angle conditions. The data presented here were collected from a male index finger. In our method, this data is used for interpolation. As our initial attempt at a data-driven approach, we applied bilinear interpolation to each sensor element value. By independently interpolating all pressure sensor values, we were able to obtain plausible pressure distributions. We demonstrate our method using user input from a hand tracking device, the Leap Motion Controller. As you move your finger vertically or tilt it, the interpolated pressure distribution is displayed on a monitor in real time. The calculated pressure distribution can be applied to various haptic applications that require the display of spatial haptic information.